So, good morning. We finished the discussion for chapter 4 in this Monday. So, we will continue to check chapter 5, and today we will focus on routing protocols. This is chapter 5. Chapter 5 talking about network layer again. However, we focus on control plane. And for a few pages, maybe we have the discussion in chapter 4. So later we will go through some pages quickly. So this is the quick, maybe some goal for this chapter and some quick review for network layer. And in this chapter, we will have a control plane. And control plane, then we will have the traditional routing algorithms. Later, we will check these routing algorithms. And if we want to have the extension, of course, we will go to the SDN and we will already have the SDN controller and that know how we can achieve routing using SDN. And finally, we already have the brief discussion on network management and network configuration. Of course, we already have some examples. So that here we have the instantiation that says the implementation using the internet. Well, so using the internet about the protocol after the traditional routing algorithm, we will already have these. OSPF, BGP, and for SDN we will have open flow, and we have the specific one ODL and ONOS for SDN. And about the control, actually we can have the ICMP compared to the IP. We have the control protocol of ICMP. And talking about network management, we have the protocol of SNMP and the others. So later we will have the routing protocol. For routing protocol, we have two categories. One, we need to have the global information. Then we need to have the routing based on the global information. So we have the link state routing protocol or routing algorithm. Another one, it is the distance vector. That says we have the distributed protocol. As for the others, later we will check it. And for the following pages, some of the pages we've already know in the in chapter 4. So data plane, control plane, you can refer to these. Likewise, for per router control plane routing. And in fact, we already have the per router control plane using the traditional routing algorithm. So later we want to already know these. All right, so for these, I think in chapter 4, we've gone through so here we go through quickly. All right, so I go through 2 pages quickly because we already know that, we already know those 2 pages in chapter 4. And today we have the focus on routing protocols. And actually we already have link state and distance vector later. Well, routing protocol. Currently, we based on the traditional control plane for network layer. So we focus on routing protocol. Routing protocol want to determine the path or the route or the so-called route. So how we have the determination of the route to path the packet from the source to the destination. You see, routing protocol actually want to determine Currently, we use the term good path. So determine a good path. Sometimes we need to determine a set of a good path. Also, good. Later, we will know what that means, good. Path, actually, we will have the path from the source node to the destination node. Good. So, what that means, good. You can base on the definition of a cost. Then cost, then we prefer to have the least cost. Least cost means the minimum cost. Or maybe based on the path, actually it's a travel. So we prefer to have the shortest time required to travel. So this is the fastest path. Or maybe right now, we don't care about cost, we don't care about speed or not, how fast it is. We care about, in fact, it's the real traffic path. And real traffic paths care about least congested from the user viewpoint. Well, also about good, we may have different definitions. Later, we base on cost simply because we want to have the idea how we can have the good path. And good path based on cost. And in fact, cost can cover time, can cover congested level or not. You just have the proper mapping, then you can define the cost. All of us use the definition of cost. You can cover almost possible definitions. Therefore, we base on cost to have the routing protocol. And routing, similar to the previous topics, without know routing is really important. So here, without know, it's a top 10 network challenge. Well, to have the discussion for routing protocols, actually we should have the path node. So we can employ the concept of a graph. A graph here, using a notation G, it's a graph. And here we have a node. And we have an edge. And node here. As for edge, these. So we can have a graph containing nodes and edge. So a graph to allow us to have the definition node. So we have the set to cover the nodes you want to study, and likewise cover the links to have this graph. And also you notice the numbers here, the number actually is cost. So we can have the graph, and based on the fundamental graph, we can associate cost with the graph. So later we can base on this kind of graph to have the least cost path. Therefore, cost. We have the link cost, and right now we want to define the cost. So here, link cost, and if we want to define the cost of a path, actually, you just try to collect all the costs going through, if we go through a path, all the link costs, you collect them, then we can have the path cost. If we can have this path cost, then we can find an algorithm to determine the minimum least cost path. Well, before we already have least cost routing algorithm, we already have some possible categories. First of all, if we want to study the routing algorithm, we can check information. If we want to know the complete information, then it's a global version. So we have a global. And global, of course, you can treat it is the centralized. Compared to centralized, or we have decentralized. So we have global. Or maybe you think, okay, we just use centralized. If you use centralized, another one, it should be the decentralized. So yeah, it's true. It should be centralized and decentralized. Here you can replace global by centralized by global. So we have a global and decentralized for this kind of category. Decentralized, we have the routing algorithm, distance vector, and so that you know the information about the neighbors. And you cannot know the global information. So we have a global and decentralized. And actually, how we change or how we update the routes if we have the information change. Based on time, so we can have the static one. Static, it doesn't mean we always keep all things unchanged. But sometimes we change slowly. So static means change slowly, or maybe stationary. So we have a static version. Of course, a different one should be the dynamic version. Dynamic version, of course, we can have a time frame shorter. Oh, you can feel, yes, we know something changed, then we update. And if so, then we have the dynamic version. All right, so we have these. And of course, we will have the global or static and the dynamic and decentralized possibly, or maybe a different combination. Well, so based on the possible category, let us have the discussion for the routing protocol. And we start the discussion of link state routing algorithm first. Link state. Link state, if you want to code, we have the link state routing algorithm, that's fine. And if you want to have a different description, you can skip link state routing algorithm. Instead, you can call, oh, it's a Dijkstra routing algorithm. So Dijkstra routing algorithm is equivalent to the current link state routing algorithm. All right, so you call it link state or you call it Dijkstra routing algorithm. Either one is okay. So we define how we have the routing algorithm based on link state. As for Dijkstra, yes, you can try to check the pronunciation on the internet. Yeah, I found it should be Dijkstra. It will be a suitable one. So Dijkstra routing algorithm. Dijkstra routing algorithm based on the link state to have the routing algorithm. So it is the centralized or the global routing algorithm. We need to know all the information, all right, containing all nodes. This is assumption. Maybe you think, okay, for the real scenario, we cannot have the strong assumption like this. Yeah, it's true. This is a strong assumption. And if we have the strong information, of course, we can base on the small scale. All right, for example, currently we can have the possible maybe activity within the classroom. And the classrooms, of course, for me, I can know all the status for almost know the status for all of you. So this one, it can be the assumption for the small scale network. If we have a really large scale network, then the Dijkstra routing algorithm, of course, it becomes infeasible. Well, so we know the assumption is a strong assumption. And the strong assumption actually, it can be valid for the small scale network. So if we have the centralized one, we can have the cost. And this code actually is called the link state. And the link state to reach the assumption, so we need to broadcast. broadcast so that we can have the update. And likewise, if we have the mechanism of broadcast, how about a large scale network? Infeasible again. If we have a large network and you want to focus on the broadcast, then it occupies the bandwidth for the normal activities. All right, so this one, because all nodes need to know all the information, so that's why we need to have the link step broadcast. And based on the given information, even obtained from the broadcast, then we can find the least cost path. And the least path costs from the source node to the destination node. And later for data, actually we can have multiple destinations from a single source. To have the result, we need to have the iterative procedure. So we already have the iterative procedure. And the iterative because of a single source to multiple destinations. So we already have the property. After k iteration, then we will know from the source node to k destinations. Therefore, I point out one source to multiple destinations. Therefore, we have a k iteration, then we know the least cost path to k destinations. Why we have this kind of property, later we can that you have the algorithm, then you will know, yeah, it's true. And in fact, we will have the notation, and later we will know the meaning of the notation again. But going through the notation quickly because it's helpful for us if we keep something in mind. Cxy is cost from node X to node Y, and d of v, the current estimate of cost of the least cost path from source. We have the defined source to destination v. So we just have a single source. We don't want to mention explicitly. And we just mention we want to have the cost from v to that node v. And P of v, predecessor node along the path from source to v, that says, okay, v and the previous node is the P of v, so it's a predecessor node. And n prime, previously we have n for the all nodes, and n prime here containing the nodes of least cost path. Definitely known. That says, okay, I know the least cost path for the current nodes. That says we can have a really small scale to the entire network. So n prime will change. Later we will use n prime to serve as a notation, but it will change. Actually, we already have this algorithm, and this algorithm actually is the Dijkstra algorithm. So initially here, we have the source node. So of course, the source node contained within the least cost path. It should be one of the nodes, so we know, yes, this one contained within the n prime. And for all nodes v, of course, the other nodes, all nodes v, if v adjacent means the direct neighbors. All right, so adjacent to you neighbor, so it's the direct neighbor. Then we use it to have the setting. All right, we know the least cost. Because of the direct one, so we have the link cost, right? For example, right now I'm the source node, and I can reach neighbor, and this is the least cost. As for the others, maybe, okay, maybe we don't have the direct connection. So no direct connection, we will set it to infinity initially. set it to infinity initially. So here. So let me have the example within the classroom again. Maybe direct link to the two nodes and indirect to the other. So we have the link cost for the two nodes. As for the others, we set it to infinity first. Well, this is the initialization. About the initialization, I think it's easy, right? After initialization, then we have a loop to have an iteration 1, 2, 3 till all the nodes contained in n prime, and then it's finished. So someone like will want to have the collection of nodes for n prime. If all nodes are contained in the set n prime, and then we finish the algorithm. It's the algorithm. So loop will well find W a different node, W not in n prime, such that D of W, that says the least cost from source to W, is a minima. So that says we may have many W, but the node W contains the least cost up to now. You think, okay, the minimum value associated with a W. Then we choose W, and W is included in n prime. That says 8 W to the set n prime. So we find W and put W to the set, because we have the new, something like new info. All right, so we find an info. We have the new node W. So based on the new node, possibly we can have the least cost update. What kind of least cost update? Previously, maybe we may have some update already, and currently from the source to V should be the cost containing the minimum value. But maybe how about to have one more link to have a different path from the source node to W? So we have this one. How about to allow to go through W and W to V? All right, so we can have a chance to check maybe current path and the new path, but one more hop. Here I have the term hop, one more hop. That says one more link or one more node. So how about one more link and one more hop? Therefore, we can have the update. All right, so this is a one more hop cost. If we have the second cost and compared to the previous code, which one's smaller? If we have the update that says, oh, fewer hop path is not the minimum path. Instead, one more hop is the minimum path. Then we set the minimum path and set the least cost, because yes, it's the true one. So we based on this one to have the update to have the least cost path if we have new information. And we can repeat the operation until all nodes are contained in n prime. Well, so this is the current Dijkstra algorithm. And so that the Dijkstra algorithm allows us to have the least cost path findings. So we can find, based on the algorithm to find the algorithm, the least cost path algorithm. Previously we don't know, iteration 1, then we find 1, iteration 2, and the others. Up to now, maybe you don't have any reason why we have this kind of algorithm. And later we try to implement the algorithm to that field. Yes, it's true. Based on the algorithm, we can have some idea, and that idea based on this to find the least cost path. All right, about this algorithm allow you to have 2 minutes for checking with your neighbors. All right, go and check it with your neighbors first. So feel free to have further discussion about the algorithm, and later we can have the example. Well, about the current algorithm, any possible questions? No, take a picture first. So let me have a clear picture for you. Take a picture first. Later, we need to pass on this to have the implementation. All right. So let us have the example. That's our algorithm. We implement the algorithm to have the example. Step 0, initialization. Step 0, initialization. So check your photo. Check your photo. Initialization, what we should do. All right, so what we should do. First of all, n prime. Include the source node. Here we said this is the source node. And how about the others? The least cost setting. And find the neighbors. We have a V. We have a X, we have a W, right? So we should have the direct setting 1, 2, and 5. 1, 2, and 5. As for the others, infinity. For the initialization, actually, we have this setting. And also, we have the companion information. We have a previous node. So previous node for the current node, for example, V. For V, who is the previous one? It's you. And likewise for W, it's you. And likewise for X, it's you. So this is not the initialization, but this information is trivial. So we include the trivial information for the table. And so that we can have the table, we have the step. And we have least cost. And predecessor. All right, so this is initialization step 0. All right, so step 0, it should be okay, right? And what's the next step? It's a loop. Loop says we should find which node not contained within, Next one, we should find a W. Even right now, we have a W already, but not that one. We should find a node so that we have the actual node. Based on the current one, we have the smallest one. So how to have that one? It's the smallest one. It based on this. All right, 1, 5, 2. Which one is the smallest one to have the least cost path? It should be X. So this X is the W we want to find in the algorithm, in the loop. Why? To choose that one, that says, oh, the current one X is the true one to have the least cost path, because we just consider from the source node and one hop then to X, it represents the least cost among all the others. So we can guarantee this one is the one to have the least cost. So this one X. Because of X, so we put X to N prime. All right, and so that we have the update. The update, actually, we should consider the neighbors. Oh, neighbor, if X can serve the neighbor, can we have the cost update? Because of neighbor, so previously, Y cannot reach U directly, but this time Y can reach X. And so that go to the source node. So we can have 2 for Y. Right? So we can have a 2 to Y. And how about the others? About W? Yes. W, we can have U to S and then to W. Current cost, it should be 4. Compared to the original 5, it should be 4. And how about V? V, it won't be necessary to go to X to V because 3 larger than 2. And you can check the others. But why we don't have these? Because finish. Normal update, because this one is the smallest one to X. So U to X, stop. No information update because it's the smallest one. It's the least cost already. And so that we have the new update, right? About the current step, maybe I keep the page here. Step 1 is okay. All right, if for step 1 it's okay, then we repeat. If we repeat, student in the classroom, if I want to find the W node in the algorithm, which one serves the next W node? V, Y, right? And V and Y, which one you want to choose? Either one. Either one can be chosen to serve the current W node. And the algorithm chooses one of the 2 nodes. So, because of a loop, right? And the loop determined based on these. So, which one we want to choose? V or Y is okay. And the current algorithm chooses one of the nodes. It chooses Y. Actually, you can choose V, but the current node chooses Y. And likewise, we can have the operation Y included in N prime. And we need to have the update. For the remaining, I go through quickly. You can check them. So we can continue to have the update for these. And this time, if I want to continue, V, W, and Z. Again, why stop? Because we set it already. So for remaining update, it won't be necessary. And for V, W, and Z, for the next round, which one serving as the W in the algorithm? It's V, right? So we can continue. All right, and we can continue again. W and Z, which one to choose? W. Until finally, we choose Z. Because we choose Z, and Z, should we have the update anymore? No. So, Z included only, no update for this. And that's all we can have for the table. And this table, we can find the least cost path from the source node U to the other nodes V, W, X, Y, and Z. Why? Because how many iterations? 5. Z says initialization, not the iteration. So we have 1, 2, 3, 4, 5. 5 nodes using 5 iterations. So we find the least cost path from the current source node U to the other nodes. Alright, so we have the reminder for you. If we find the node, here we have A. 8A to N prime and update the least cost path from source node A to all the possible nodes known. Even it's infinity, we need to have further update if we allow the path to go through the current node, chosen node A. Alright, so this is the current example, Dijkstra algorithm. And the table, you can check a few steps. Initialization currently okay, right? Step 1, it should be okay, right? And the others. So you can check the others. Later you can check how to have the update there. But based on routing, the Dijkstra routing algorithm, we can have the table. Based on the table, why we have the least cost path? Actually, we have the reverse direction. Alright, we can pass on the table and pass on the table to have the reverse direction. For example, previously X. As we have the least cost. Sorry, not this one. As we have the least cost first. So as it should be U to X. So we have it. And next one we choose Y. Y, how to have a Y? Reverse direction. Alright, Y should be previous one, it should be X. And here X, previous one, it should be U. So we have Y to X and to U, but the real one should be U to X to Y. And what's the cost? The cost should be 2. So this one contains and furthermore, we have X, we have Y, and furthermore we have V. V actually it's a single one, V to X. And furthermore, how about the next one? It should be W. W says, oh, okay, W to Y. So at least 8 that link W to Y. And finally, it's Z. Z says Z to Y. So we have this. So this is the spanning tree. The spanning tree allows us to have the least cost path from U to Y, U to X, U to Y, U to Z, U to W, and U to V. And in fact, this is the spanning tree. Based on the spanning tree, we know the least cost path from source node U to the other nodes. Alright, so as for why it's called a tree, you can base on the data structure. So you will know the meaning of a tree. So this is a spanning tree, the spanning tree that you have for the least cost spanning tree. Alright, if we have the least cost spanning tree, then talk about this. Alright. If we have a DW, alright, so DW, so what's that one? Okay, that one maybe we'll forget it. And if we have the spanning tree, then we can list U to V. We have the cost. Oh, sorry, it should be 2. And you can have U to X and U to W. The path should be U, X, Y to W, and the cost, the path. What's that? You can have the accumulation. It should be this one. It's oh sorry. Here, it should be 3. So you can have the way to find the minimum cost, and you can find the path using the reverse direction. If so, then about forwarding table. Alright, about the forwarding table, how about if we want to forward the datagram to U? If U, the outgoing link should be UV. So we have these. As for the remaining same, so this is a forwarding table. So we can have the least cost path, and we can have the forwarding table setting. And likewise, based on the spanning tree, how about the forwarding table for Y to Z and Y to W? We know the path explicitly. Alright. Okay, so this is another algorithm. At this moment, I reserve it for your after class exercise. Alright, so you can use the example to check you understand the Dijkstra algorithm or not using the current example. So I skip it. This is the answer. Alright, so this is the answer. You can check them. Well, I skip one example because it's a different example. But the different example asks you to apply the Dijkstra algorithm. And we have the discussion. If you have the background of data structure, or algorithm. So you have the background of data structure or algorithm. Then we can have the complexity using big O notation. Well, maybe you don't have the background, so I mentioned we can have the data structure to have the big O notation, or the algorithm to let it have the big O notation. So I already have the information. I skip it, and I mentioned the efficient one should be this. Alright, log order of n squared, not so good, but order of n log n is the better one. So we have the information, but I skip the detailed information. And likewise, here, this is the, you can think, this is a time complexity. For the upper part, this is a time complexity. And for the message part, you can call it the space complexity. But currently, we have two types of the complexity. You can check them, but I didn't know this one, you should base on the structure or algorithm, then you can check these. But I mentioned one important phenomenon, acceleration. Acceleration means this one. Acceleration. The path will change if we have some special cause definition. This is the phenomenon, acceleration possible. If we define cause as the traffic volume, yes, you just consider the real case when you try to find a path for the daily life to maybe going to your home. All right, going home, then you need to find a suitable path. You want to find the path based on this, maybe this traffic volume. And that one will cause the acceleration. Something like will based on the traffic load. So, well, for the current consideration, we assume we have a traffic load 1 and 1 and E. And assume we have the current routing. Oh, we choose this one, so we have a E. We have a E and 1, so we have a 1 plus E. And here, no, it's 0. And here it's 1 and it's 1. And we have the two directions, so we have the association. But next time, how about this one? All right, so we want to choose, oh, we have a 0, so we want to go this one, 0. Not this one. Because we have the smaller cost. All right, and as for E, for some reason, we will choose this. And for 1, we will choose again. So we change the path. Oh, sorry, maybe we still continue this, but we change this. And likewise, we have the new update. And also the others. So, acceleration here. All right. Okay, so about the phenomena, you can check it later. Today, we finished the routing algorithm, just the link state routing algorithm. And we already have the algorithm and the implementation, and reserve one example for you, serving as the after-class exercise. You check it later. All right, so that's all before you go. Let me make sure any questions. If not, see you next week. Bye-bye.